Okay, I want to talk a little bit about the normal curve so that hopefully we have as good an understanding of that as possible. So you can see here on your screen that we have a picture of the normal curve. I'm going to make this a little bit bigger so that we have a really good picture of it. And we don't need the stuff with the words on the left side. And I also want to direct your attention just to the top part. So what I'm going to do here is I'm going to like highlight this underneath, because everything that's in this highlighted portion, I want you to sort of just ignore that. Pretend it's not there for the moment, because we don't need it for our purposes right now. All right, so that is gone. It doesn't exist. We're not paying any attention to it. So when we look at the top part of the curve here, what we've got is in the very center here. Let me get a different color. In the very center, we're working from this center line out, which would be the mathematical average or our mean. We're working out in both directions. If we're going to the right, we're going in a positive direction. See this positive sign here? And if we're going to the left, we're going in a negative direction. So let's say that we want to find out, or maybe we don't want to find out. Let's just say we're going to measure the feet of all the women in the United States, or let's just take their shoe sizes. That's a little easier. So let's say that we do that, and our data says that the average shoe size for a woman in the United States is an 8. So right here, this line is going to be shoe size 8. And if it's the average, we're going to have more people 8 than any place else, which is why this is the highest point of the curve. All right, that makes sense, right? Because we've got lots and lots and lots and lots of people who have shoe size 8. Now, if I have the shoe size 9, I'm going to fall on the right side of the curve, because this is the positive direction, remember? And if I have the shoe size 7, I'm going to fall on the left side of the curve, because that's below average, and this is the negative side. All right, so that's pretty simple, right? So what mathematically we know, according to the curve, is that if we take this enormous sample of shoe sizes of women in the United States, that 34% are going to be in this area right here, and another 34% are going to be in this area right here. So 34.13% is going to be on the positive side of the curve, right next to the mean, and 34.13% is going to be on the left side of the curve, right next to the mean. Now, down here at the bottom, notice this is 1, and this little sign here is standard deviation. So all of this area here between the mean and this little line is 1 standard deviation plus or above the mean. And this little line here, which I was trying to go over, can't see very well, evidently, all of the people that fall here are in that first standard deviation below the mean. And what we know theoretically is that 34.13 plus 34 well, I gotta put the numbers right here. Oops. 34.13 equals 68.26, right? So what that tells me is that 68.26% of all the people, all the women in the United States will have a shoe size that falls between one standard deviation below the mean and one standard deviation above the mean. So whatever size that is, it's going to be in here. Now, if we are really exceptional, I want to erase this because I need more room. So, whoa. All right, a little snafu there. Let's find where we were. We were here. Okay. All right, what was I going to erase? I was going to erase, I think I was going to erase some of this stuff. Get that off of our screen. All right, so that looks a little better. So let's say we want to look at, like, we're really exceptional, and instead of being right here at the middle, or in this 68.26% here, that's our one standard deviation above and one standard deviation below, right? So instead of that, we want to look at somebody that is a little more exceptional, right? Not quite so average in the middle. So we might come over here. So these people, there's going to be 13.59% of them that actually fall here. And my finger is really fat. So 13.59% are going to fall between one and two standard deviations above the mean. All right? So 0 to 1, 1 to 2. Same thing over here. We've got another 13.59% that are exceptionally small. So these folks are exceptionally large if we're going with the shoe size thing. If this is an 8, these folks are going to be one standard deviation above the mean. Now we're getting larger and larger and larger. This is we stand out more because it's not as average. Okay, so we know that. Then we've got our 68.26, right? That is the green. And then we've got 13.59 plus 13.59. 2 times 9 is 18, right? 5, 10, 11, 6, 7, 27.81. So we've got 27.18. I misspoke there, sorry. Erase this. All right, so in the orange, we've got 27.18. So the green represents 68.26% of our sample, and we can generalize that to the population if our curve is more or less normal. We know also that if we include the area in orange to the right, that adds 13.59%. If we include the area in orange to the left, that's another 13.59%. Together, 27.18. So I'm going to add those up. 14, 4, 15, right? 7, 8, 9. So 95.44% of the population is going to fall between here, 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 and here. So if we are saying that somebody is 2 plus standard deviations above the mean, they're pretty exceptional. they're different than 95.44% of the population. Same way, if they are falling between 2 and 3 standard deviations below the mean, they have exceptionally small feet. Exceptionally small. Because according to this, only 2.14% of the population is going to fall in this area, below the mean or above the mean. If we were to print this paper out and we were to fold it over right down the center line, it would be identical on both sides. So the math theory behind this is that we can look at any sample as long as it is representative of the population. If we look at that sample, we can see where the sample, like the data falls from the sample, and from that, we can generalize that information to the entire population. And that is what the normal curve is really all about. It's about the math that allows us to generalize from our sample to our population. We can do that as long as our data are fairly normally distributed. When it becomes very wonky like data that's distributed very wonkily or crazily, then our assumptions that we can generalize that to the population become a little more compromised. Okay, so I'm going to erase this because I now want to talk about standard scores. We're going to talk about that a little bit down below. So I want you to see this. We can use the curve and we can find out where any particular data point lies. Why would we want to do this? Well, let's say that we take a test like the GRE or the ACT or something like that. And we get a score and we want to know how we compare to everybody else. So we can figure out where that score lies on our curve. Maybe it's here. Whoops. So I have the eraser on. Maybe it's here. Maybe it's here. Maybe it's here. But in order for it to make more sense to us, to know sort of how we compare, we have to be able to figure out where we are in comparison to other people, other test takers. So one way we can do this is we can use standard scores. And I want you to look down here at z-scores. Z-scores are one of the most useful types of standard scores that we have. And they're also used in the calculation of other standard scores like the t-score. So we're going to talk a little bit about that in another tutorial, but I want to introduce that to you so that you understand that it's just another way of saying exactly the same thing. So I could have said all of this in English, which I did. I could have said all of it in Spanish. I could have said all of it in Italian, but I'm saying the same exact thing. And it's the same way with z-scores and t-scores and percentiles. It's just a different language, but we're saying the exact same thing, and we're using the bell-shaped curve, the normal curve, to do that.